And we're gonna test. Testing. Oh, I see it moving, so sound is working. Share is working. All right, so we're gonna do topology today. So that's where we take a SolidWorks object and we optimize it. So that means we're gonna do some simulation stuff like putting loads on it. We're gonna constrain some areas. So what I did as a test the other day was a table is by far the easiest thing to do. So I think the assignment says do a table or whatever else you want to do. Okay, so if you want to find another object or a different shape, go for it. You can optimize any shape that you want to do. The goal is to allow SolidWorks to do a finite element analysis on a structural thing. So FEA is determining where the stress paths are in an object and then building material around the stress paths and letting the software determine where to put the legs and how to do it. So this is a table I defined, and I'm not even sure you would have to. I did it with a loft. So 2 sketch loft, right? 1 sketch up there, 1 sketch down here, but it was the same. I didn't change the diameter. So I don't think that was necessary. It could have been just an extrusion, right? I did put feet on it because if you don't do that, you can't identify regions that you want to stay, right? If I just did one big round at the bottom and I said, okay, that's a preserved region, then you're gonna have a big round at the bottom and it doesn't create legs and it wouldn't know what to do, okay? So what I wanted it to do is like, okay, here's the regions that I want to preserve, and then I want to preserve the top, and then I'm going to put a load on the top, and then it's going to determine like where material needs to be stable. And I put a distributed load on top, right? And this is what it gave me. And I printed it this morning, right?
Cool.
So that's an optimized table that uses SolidWorks artificial intelligence for finite element analysis to determine where the stress paths are. These are the regions that I preserved, those rounds. And wherever the load goes, it automatically preserves. You don't have to preserve that. Okay, now if you look at this closely, the feet are shifted. And I don't know whether that was the print or whether, oh no, I can look here. So here's the topology study. Oh, I know. Maybe I did something. Oh, topology study. My results are gone. Wouldn't you know it? Maybe it'll come back. There it is. So that's the first one I did. Right? Oh, and I did shift them. That's interesting. I don't know why it shifted that a little bit. It's probably in the preserved regions. So I probably didn't need to make these thick either. We probably could have made them really small to have my preserved regions. Anyway, I've only done a few of these, but it's super cool. Now it comes out like this and then you can smooth it. So in the mesh area, you can go into the mesh and create smooth mesh and smooth things out. So we'll do that. Yeah.
Part of that, the one that you kept that 3 circles, if you notice, right, the structure itself was shifted to the inside, not to the outside. When I saw the figure itself, the table that you built, you know, I thought it was
They're all shifted to the outside.
I think what it was is the material, the legs itself shifted to the inside. If you see it from the front view.
I'm not understanding what you're saying. Because this is exactly the same as that.
Yes,
Okay.
but okay, can you put that on the front view instead of if you get it closer, zoom in, you see the structure itself, was shifted to the inside. So I think the circles itself is the same, see? The same dimension that you actually built it on. So in order to balance the weight and the center of mass, I think the program itself shifted in for the legs itself. Go to the previous one view. See what I'm saying?
I do. I mean, I totally agree with what you're saying. But I think if the software setting is set correctly,
Or it would be centered.
yeah, I don't think it would. Maybe it is needed. It
what I'm
doesn't make
thinking-
sense because this isn't hitting the ground. So
Yes. What
it
I'm
doesn't
thinking
make
is
sense.
that the program itself, what it did is actually found the center of mass and balance to build the legs. That's what I'm thinking happened.
It definitely did. It has to do that for sure. Although if you put 4 legs, it'll do all 4, right? And if you put 4 legs not symmetrical, put them anywhere, it'll also do those. So those preserved regions are preserved. It's not going to move them. So, but it will add material as you need it. So, all right, let's go through how to do it. And then we can talk about your second project. You have 2 projects. So I think I'll just start with this. This is just a model, right? So a normal model, it's a normal part. It's not an assembly. You can only do this on parts, not assemblies. It really gets, oh, this was 1 hour optimization. It takes it a long time to do this. So I'm not sure why. I even added a symmetrical plane, which I'll show you, which is supposed to reduce the optimization, but this took an hour to run it. So just beware. If you get too cute, it'll take a while to run it. I literally just started it and then walked away, came back in an hour and it was done. So I'm sure there's a number of things that can go wrong, but if it starts the topology, it'll probably complete it. All right, so it's in simulation. We're going to do a new study. So this is one study, right? And the topology study is right here. So it's down in the insight area. So when you click on that, it kind of walks you through like different topology, like a design study or topology study. We want the topology study. It's going to name it topology study 2 because I already have topology study 1. So once that happens, you get the topology kind of menu over here. So this is like where the history tree used to be, right? In parts, that's all right here. But now we get the topology study menu. And you kind of just work your way through this thing, okay? So the very top is what it is, topology study. This one is its name. If you right click on it, you can see the information underneath it. So the first one, it's good to set your material. And it wants to have a material because it's going to run the stress analysis based on the stress of that material. So I really wanted to do wood on this one, but I was afraid, so I did steel. Because I didn't know like what it would do. But I think on this one, I'm going to set it to wood and we'll see if it even starts. We'll go with pine. Yeah, see, it needs Poisson's ratio, it needs yield, it needs Young's modulus, it needs all these things, and it's not in here. So I'll say okay. And it's going to say no to that. So let's see if any of them have it. So I could go research it and put it in, but I'm not doing that right now. Oh, balsa, it took it. All right, we're going to do a balsa table. All right, next one is connections. So in the connection area is You can do a number of different things. If there's like bolted connections in your part or something like that, you can set that up. I don't have any of that. So fixtures. So this would be a fixed geometry, a geometry you didn't want to change. So the example, if you go through the tutorial, is a bracket with some holes, right? So they fix those holes, so it can't mess with that, right? I could fix the top. I don't need to do that because I'm going to put a load on here. And I could fix the bottom. I don't need to do that because I'm going to preserve it. So this doesn't have any fixtures. But if like you're going to do a bookshelf bracket, you know, the triangular bookshelf brackets, you could make a solid one of those, but it usually has bolt holes, both top and bottom, to put the shelf on and to mount to the wall. You would want to add a fixture to that and fix it. So it doesn't move that stuff around, or it doesn't eliminate the hole because it's reducing material, right? That makes sense? All right, no fixtures. I do have loads. I got to put that on, and I'm going to do a pressure load or a distributed load. So it wants to know where. I'll put it here, and then I made it PSI, and we made this wood, right? I'll do 5. I'm just gonna do 5 PSI. That's 5 pounds per square inch, right? So that's still a lot of weight on this thing. Maybe I should do this. I'll do 2.
Is it balsa wood?
Yeah, it's balsa wood. It's gonna end up with a big block. That's your option.
Made out of like those
Oh, that's not gonna be great. All right. So now we have a load, and then the goals. That's like why we're optimizing, right? So the top one is really the only one I'm familiar with, and that's the best stiffness to weight ratio. So that means I have the opportunity to take this thing, which is obnoxious table out of balsa wood, right? And reduce mass by a certain percentage. Now, I did 30%, which I didn't think was a lot, but he gave me that. For a 30% reduction, I feel like that's more like 30% left over. So
Yeah.
I think that might be what it's doing is if you say 30%, we're keeping 30%. And that 70% is reduced. That could be why this shape is taking so long to optimize because we're removing so much. So you could build kind of a bulky shape that's closer to what you want and then optimize that. And it would have to remove less material. Does that make sense?
Mhm.
Like I could put the 3 legs in like this big around or something. And then it's gonna like have a lot less material to reduce. I think that might increase the,
Rather than starting.
yeah,
with
it
like
might
a
just go faster. Yep.
shape.
So when you say yes to this, it's good to go. That's what you're gonna constrain. There's more that you can do, like, you can minimize, maximize displacement. That would be like deflection. So you can control that. There's other things you can set up. The manufacturing is add preserved regions. This is where you preserve the feet. If you don't do that, it's just gonna do whatever it wants and it's gonna ignore the feet and just go for it, right? So preserve regions, that's here, here, and here is what I did. Because I was hoping it would just, go all the way to the bottom. It really didn't though. It went to the top of those extrusions. So I think if I was doing it again, I'd probably shrink those up a little bit and get them really small. Why is there 3 faces? Oh, there is 3 faces. Okay. So when you have all that set up, there's create mesh. So the last one is mesh. And what that does is it essentially creates the finite element analysis sizes. So there are small elements that they're going to do this with. And it's going to create that mesh. And you can set that mesh to different densities. You can make it more coarse, more fine. Right in the middle is just where it was. So it says right here, a high quality mesh is recommended for a stress factor of safety constraint. So it creates the mesh. Right, so that's creating all the little nodes that it's going to do the analysis with. And then you run it. Run, right there. If it starts, that's a good thing. If it gives you an error, then it has a problem. No loads or boundary conditions. Not sure why it's telling me that. Have a load.
You have to add the existing road on the back of it.
Nope. Well, at least I didn't on the first topology. I just had load on the top. I wonder though. This makes sense. First direction, non-uniform, simple settings. I had a face in there, right? It was like that before. See if it gives it to me again. So here's the first one. And there's the load. It added that. That's the preserved region. That's interesting, isn't it? MPSI, yeah, no other setting, normal to surface, okay. I did fix that geometry, that's right. So I added a fixture. Let's see if that was it. Ah, I went right by fixtures. Fixed geometry. That was it. So fixtures. And preserve region.
Your other one has a stress constraint.
Yeah, it made me add that, but I think that was because of the steel. Also didn't make me add that. It said for a good topology study, add a stress constraint. So. Pretty sure that's because it was steel. Wood didn't make me do that. See if it runs now. Yeah. Looks like about the same time frame. We'll let 1% go and then see how much time. That was faster. It was like, what, 18, we'll say 20 seconds at 1%. So this might run a lot faster. Right, so that's the job. And then you're gonna upload that. And then the second one, I haven't written up yet, but I'm gonna show it to you. So the people that are not here, I don't know how this is gonna work. I'll have to get them the information.